He has taught control system and missile control over 30 years with the Defense Institute of Advanced Technology, DIIT Pune, and teaching a control system from 11 years in COEP, in the Department of Instrumentation and Control. He has over 90 publications in more than 90 publications in the international journal and reputed conferences, and his citation is around more than 1500. Now I welcome Professor Phadke. I request him to please share your presentation and start discussion. Thank you, sir.
Thank you, Dr. Amruta Deshpande. It's a pleasure to be with you all on this FDP. And as the topic is announced, I'll be talking on sliding mode control in the morning now. And later in the afternoon, I'll talk about disturbance observer. Rather than giving you only an overview of things, although we don't have much time, even then, I'm trying to give you the essential basic design of SMC. So with that in mind, I would start. But before we start and go to the sliding mode control proper, we need some background, some overview of what we normally consider as feedback control. So with that in mind, I'll now go to my presentation. So we'll be talking about... Sorry? Hello, am I audible to everyone?
I request to all participants to please mute your mic.
Yeah. Is this okay now? Can everyone hear me?
Yes, sir.
Yeah.
Yes, sir.
So,
yes. Very good audible.
Yeah, I'll be talking on sliding mode control. And before we go over to sliding mode control, a quick overview of basic ideas in control is what I will start with. So a quick overview of feedback control. And whenever we talk about feedback control or systems, the modeling issues come into picture. And modeling and their limitations. Modeling is always imperfect. And therefore, what limitations are there for modeling, that also we'll discuss. I'm getting an echo. That might be somewhat nagging to others as well. A big echo is coming. Is it okay with everyone?
Hello. Request to all participants to please mute your mic.
Yeah.
Madam, Amrita ji, I think you can mute everyone, madam. Let us stretch. You can mute everyone by one go.
Yeah, I think that will be better.
That will be better, madam. Madam, Amrita, madam, you can go to the top section. You will have mute all. Option will be there, and you can make already this.
Okay.
Amrita, mute to everyone and give the control to Dr. Phadke.
It's done, sir. It's done.
Okay.
Yeah.
Okay.
So the main control approaches we would like to just briefly touch upon and then come over to sliding mode control. So, although most of you have already done feedback control and therefore these things are not new to you, even then, I would like to give a basic idea for those who may be altogether new to feedback control. And that also brings us or develops a continuity for the discussion. So I'm considering here a simple a simple system actually, which is a room which is heated by a heating coil. And the idea is to keep the temperature in the room equal to the desired temperature. So we want the actual temperature TA to be equal to T0, and for that purpose, we have got a source, a switch, a heating coil, and an adjustable resistor. But with this arrangement, there will be flaws. If someone opens a window or there is a shower outside all of a sudden, then the temperature will not be maintained at the desired temperature, and therefore we make a modification in this way. Everything else is same, but the thermometer in the previous transparency is now replaced by a bimetallic strip here. This is the bimetallic strip. And this bimetallic strip, as we all know, has the property that if the temperature exceeds a certain desired temperature, certain set temperature, the bimetallic strip bends to the right. If it bends to the right, the contact is broken, heating is discontinued, and the temperature will come down from the temperature that was higher than the desired temperature. So, this system, the basic difference between this system and the previous system is that in this system, it is the difference that activates the system. So, that's the idea of feedback control. Now, if I put it in a general way, the two systems, the first system was an open loop control system where the heating produced an effect, heating produced a temperature in the room. But if that temperature, if that effect was not satisfactory, nothing could be done to the cause. Whereas the second system, which we saw, is a closed loop system because not only does the cause affect the plant and produces an effect, but the effect in turn has an a feedback to the cause. So in the first system, the effect depends on cause, but in the second system, cause and effect are interdependent. So that's the idea of closed loop control. Cause and effect are interdependent. And this situation can be viewed slightly differently in this way. A closed loop system where a cause produces an effect and that effect in turn can alter the cause is equivalent to two systems. We can look at them in either way. Feedback modifies the cause, as we can see here. Because of the feedback from the effect, it modifies the cause, acts on the same plant, and produces a desired effect. On the other hand, one can look at the whole thing as feedback modifying the plant rather than modifying the cause. As we see, when we take proportional derivative feedback, the plant itself is modified in a certain sense. So it's a matter of choice. It's a choice between how you look at the feedback control system. So either way, one can take a look at the feedback property. The feedback essentially gives us freedom from having to know a lot about the system that we want to control. Now, what you see here is the general block diagram of a feedback control system. Most of you are very familiar with this block diagram. We have a plant here, and that plant is the object of control. It is affected by disturbances and uncertainties. No plant is free from uncertainties. We don't know enough about any plant, however simple that plant may be. The output of the plant, as we have identified, whatever we are interested in, is called the output, and the actual output is what is shown here. In a feedback control system, you measure that actual output through a sensor, the measured output is fed back and compared with the desired output to produce an error, which acts on the controller, followed by an actuator, and that affects the plant in such a way that this error, which you are seeing here, that should go to zero, or that should be as small as possible. Now, this would all have been very simple had it not been for these two players, a disturbance or disturbances, which are unknown, external, and unmeasurable. We cannot measure them. And uncertainties, that is our ignorance about the plant dynamics, plant's mathematical or otherwise whatever description it has. So it is our ignorance about the plant that is represented by uncertainties. And these two players make the job of feedback control difficult. The basic classical feedback does make the plant relatively less sensitive to disturbances and uncertainties. But depending upon the plant and its application, that may not be enough. And that is why we'll be considering some control strategies and particularly sliding mode control. Right. So, whatever we discussed just now can be considered to be a to be an interplay between modeling, which represents whatever we know. Whatever we know is put in terms of a model. What we do not know is called the uncertainty. Uncertainty may be large, it may be small, or whatever. By uncertainty, I also include disturbances in this. So this is actually uncertainty plus disturbances. And what we have in our hand, that is called the control. And there is an interplay between control and modeling and uncertainty, and control and uncertainty. It might look odd as to how control can change modeling, but depending upon certain control actions that we intend to take, the model may be enough, adequate, or not adequate. A simple example, which we all know, is if we take a large control action, then the actuator may saturate. And in our model of the actuator, if we are not considered its saturation, that model does not remain adequate. So there is an interplay between control, modeling, and uncertainty in a feedback control system. It can be considered to be something like the Russian 3-horse driven cart, Troika, which you see here. A cart driven by 3 horses. So the situation is somewhat similar to that. Okay, now just although we talk about these terms uncertainty and disturbances, and they look very simple terms, some examples of uncertainties and disturbances are in order. And if I consider a missile as an example, a missile system as our plant, then what are the uncertainties and disturbances that we might expect in a missile system? Well, in a missile, most of the mass, especially the long range missiles, most of the mass is in terms of the propellant. And the propellant is stored in the rocket motor, which may be placed somewhere here. If the missile is a long range missile, then the propellant may be 90% of the overall mass of the missile. And as we know, for a missile to fly, the propellant must be burnt. So, as the propellant burns, the mass of the missile decreases. So, there is a big change in the properties of the missile, in the mathematical model of the missile, because a very significant parameter is continuously decreasing. Apart from that, The location of the CG of the missile also may change because the mass is changing, and the aerodynamic forces which are centered at the center of pressure, that location might change. If the difference between the locations of CG and CP changes, that affects the static margin or stability properties of the missile. Apart from that, missile is launched from sea level and goes to a higher altitude, which means the density of air changes. Also the velocity will change depending upon when the propellant gets consumed, acceleration phase is over, and velocity start dropping, then the velocity will also change. So these parameters change, and that causes a big change in the mathematical model of the missile. Besides, how they change is somewhat uncertain. We cannot say precisely as to what will be the mass of the missile at a given instant of time. So, apart from the uncertainties, a missile might face a disturbance in the form of a gust of wind. So, uncertainties and disturbances in a missile system are uh, quite something of magnitude that needs to be appreciated. Another example, which is a simpler example, is that of an active suspension system for a quarter car system. So the picture that you see here is the suspension system of one wheel of a car. And you can see that the system is comprised by the masses, MS, which is called the sprung mass, that is the car cabin and where the passengers sit. MU is the unsprung mass that comprises the chassis and other parts around the wheel. So that is called the unsprung mass. Between the sprung mass and unsprung mass, we have got suspension, passive suspension by a spring, as shown here, or a damper. And the wheel itself is like a spring and damper, and the coefficients of spring stiffness and damping coefficient of the wheel are represented by these things here. So, where are the uncertainties in this system? Well, in the first place, the sprung mass won't be constant. It will depend on the passengers that sit. Some may be very heavy, some may be light, or the number of passengers might change. On one occasion, you may have four passengers. On another occasion, there may be only one person driving the car and no one else sitting. So, this sprung mass has uncertainties. The spring coefficients and the damping coefficient KSCS will experience some wear and tear, and therefore their properties will also change. Apart from these uncertainties, there is a big change that can be produced by the road input. The road may not be level road, it may be a profile which might be changing, it may be a rough profile, there may be a bump or a dip, or it may be a rough road, and therefore the road profile acts as a disturbance. So uncertainties and disturbances. My next example in this is missile target engagement geometry. And here you can see that the missile is to be guided in such a way, the missile is somewhere here going into the screen, and the target is somewhere here going into the screen once again. The target acceleration is 80, which is unknown. The missile acceleration is something that we can produce. So this is the control that we have in our hand. Uh, Now, the navigation laws very often really need the target acceleration, but target acceleration cannot be measured because the target is an enemy object and the target may try to take evasive action. And therefore, the navigation laws suffer in terms of the performance on account of target acceleration not being available. So, if we have some method by which we can find out the target acceleration, that will be a big thing. We have done some research on this line, and we later on we are going to talk about disturbance observers. So we had used a disturbance observer to actually estimate the target acceleration, and that produced a big change in the performance. So as I was telling you, the control here is in terms of the missile acceleration, the missile system that we have. There we can produce an acceleration. So control part, uncertainty, disturbances, these are explained. And in the previous example, the control is here. In an active suspension, you have a control between the sprung and unsprung mass to push or pull the sprung mass in such a way that the acceleration of the static position of the sprung mass, that is xs double dot, double derivative of the position, will be as small as possible. So this is the control that we have in our hand. In the example prior to that, well, on board the missile, there are control surfaces, such as something like this. Yeah. So there can be control surfaces on the missile which are moved, and they cause a change in the acceleration of the missile. So we have got control in our hand. Uncertainties and disturbances are something that we do not have any control over. And by writing the equations of the missile, the suspension system, or this engagement geometry, we try to get a model as accurate as possible, but never really accurate enough. So that's how it is. Okay, a bit of history about how people develop control algorithms or control laws in the beginning. And as we all know, the steam engine governor, first invented by James Watt, was one of the earliest applications of feedback. Some applications before that were also reported, but we'll not go into that. So, steam engine governor was first proposed by James Watt in 1788. The basic principle was so good that even in today's steam engine governors, we find some sort of ideas, some ideas of this early steam engine governor. Now, when the steam engine governor was invented by James Watt, he did it absolutely by intuition. That means he did not use any model at all. So, no question of talking about uncertainties in the model. The steam engine governor produced or invented by Watt worked fantastically in the beginning, and people were very happy until sometime later when the governor developed unstable operating conditions under some environments. So people were thinking as to why the governor is becoming unstable, but could not find any reason by just the physical analysis of the system. This all happened until Maxwell. We are familiar with Maxwell because of Maxwell's equations of electromagnetics. He wrote the equations of the governor. That means he developed the model of the governor. And the stability of the steam engine governor was first analyzed by Vishengradsky in 1876. So that is how the steam engine governor was analyzed, by developing a model. Until then, the concept of models was not very popular. Nobody paid much attention to it because people develop such things intuitively rather than by a thorough analysis. That's okay. This situation continued for quite some time, as we'll talk about that later. But the modeling which is of very great importance to us because we start with model based control and we land up with the difficulty that models are having error, models are not accurate, and therefore what control strategy.
வந்து எருவெல்லாம் அடிச்சிருக்கான் இல்ல
Hello, any question? Does anyone have a question? I'm not getting that question.
அதான் சொல்றான் plan
Maybe sir,
பண்ண-
it's a noise.
Okay. Right.
ஏய், என்ன போறா வா இங்க வா திரும்பி சாப்பிட்டு போ
Sir, I am unable to mute that person right
Okay,
now.
okay.
ஏய்
So
உட்காரா பாருங்க எதுவுமே சாப்பிடாம போறீங்க
the basic modeling scheme is what is shown here. We are interested in this modeling part because of the imperfections in the models and how to overcome those imperfections. That is our topic. So we have a system, a physical system, as you can see here, this block. On this system, we make our observations, we analyze that system. So we have a system, we make observations and analyze that system and hypothesize a model. That means we make a sort of judgment on the system's performance. Those equations are called a model. On that model, we perform a simulation and predict results for which we had not previously done any experimentation. Now, going back to the actual system, we perform a real experiment and get a real result. We compare the real result with the predicted result. The difference between the two is modeling error. If the error is large, then we have to go back from here and change our hypothesis. So that is where we must go and change the hypothesis, predict results again until we get a small modeling error. Well, while this looks fine, many times we cannot make the modeling error too small. And therefore, we have to live with models which may have uncertainty in the real practice. And that is where the control engineer comes into picture, or our control methodologies that we are going to see today. They come into picture because this modeling error cannot be made too small. If it were possible to make it zero, well, there was no need for sliding mode control or any other advanced control strategy. Okay. The models that have been developed can be classified as analogy models, and many examples are already known to us. The scripts of Chinese, Japanese, which are pictographs, where what we intend looks similar to the script for it. Sun might look like a sun, a moon might look like moon or mountain, etc., etc. More useful models which have the analogy principle are the scaled down models of ships, aircrafts, dams, riverbeds. CWPRS that we have in Pune, close to Kharakvasla, does some such work on riverbeds and dams by building their scaled down models, scaled down versions of those real systems. So that is one way. In fact, I got some examples of that. The Taj Mahal that we see in presentation shops, gift articles, they are actually scaled down versions of the real Taj. So that's an analogy model. A wind tunnel that is used for testing of aircrafts, missiles, and hydro and dynamic tanks for testing ships and torpedoes, etc., etc. Well, there are systems like this where the object to be tested an aircraft is actually a scaled down version of that aircraft, something like a toy. And instead of flying the aircraft, real aircraft, what they do is fly air around that object where we have these turbines which produces that air, and a small experiment of that type which was done in Institute of Armament Technology where I was working. Well, here you see that there is an aerofoil here and the air will be coming from this side. So, oh, pardon me, I wanted to show it, show an arrow. Okay, so air is coming from left to right on the screen, on your screen, and that is how the scale down airfoil. Airfoil is actually a control surface on a missile that is being tested. So these are all analogy models that are very useful and are used even today. But in earlier days, the importance of analogy models was not really understood. In fact, while we were talking about the model of the steam engine governor, somewhere around that, after Maxwell wrote those equations in 1868, in 1875, the British Navy launched a ship called Captain, and it was launched with great fanfare. One British engineer was unhappy. His name was William Reed, and he had performed experiments with a scaled down version of that ship and concluded that the ship will overturn even in mildly rough seas. Unfortunately, no one paid any attention to whatever he was saying because his scaled down version of the ship looked like a big toy. They said that he has made experiments with a big toy, nothing else. As ill luck would have it, the ship did sink on its maiden voyage, and some 500 people perished. Okay, so those days are gone. Now the scaled down versions, analogy models are taken very seriously and absolutely used before a mathematical model is attempted. Apart from the analogy models, the more important and more prevalent, more popular models are the symbolic models. And scripts like Devanagari, etc., are an example. But symbolic models are writing mathematical equations for a physical system. Mathematical equations can be differential equations or difference equations. And for those who are very familiar with control systems, they know that differential equations, in particular state space equations, first order simultaneous differential equations or transfer functions, are used as models for control systems. So we'll be using the mathematical models, the symbolic models, for the simple reason that is apparent here. You can see here that there are two systems, two physically different systems. One is a mechanical system with mass, spring, and damper, and another is a purely electrical system with inductor, capacitor, resistor, etc. So physically, these two systems are different. But when we write differential equations for these systems, we find that the differential equations that govern a mechanical system like this is a second order differential equation with fairly constant coefficients, mass, damping coefficient, and spring stiffness. And the electrical system is also a second order differential equation with inductance, resistance, and capacitor fairly remaining constant for a small duration of operation. So, if I can analyze a mathematical model, if I can analyze a second order differential equation, no matter what system I'm dealing with, I'll be able to make conclusions about their performance. So, that is why this property, unifying property of mathematical models, is very important property. Now, all models have a domain of validity. This is another reason why we talk about being able to control uncertain systems. That means even if I make a model and even if that model is good, under certain conditions, the same may not hold good when the operating conditions change. For example, the spring. We know that the spring force is proportional to the deflection, normal law for spring. But if that deflection exceeds a certain value, then that law no longer holds good. Then it is called a hard spring or soft spring. The people in the audience who have got mechanical background will agree with me that if the deflection exceeds a certain value, then the linear model will not hold good. So once again, that interplay part I'm coming back to. If you have a control law such that this spring deflection is kept within a certain value, then the model is good enough, kx is good enough. Otherwise, your model needs to be changed. So there is an interplay between control and model. Similarly, saturation, about which I have already talked, saturation of actuators, amplifiers, and whatnot. We have got saturation in most of the things. And flexible body effects in uh, aeronautical objects such as missiles or aircrafts. A small or a short missile, maybe a shoulder fired missile like an anti tank missile, can be considered to be a rigid body like this. But a long, thin missile, the one that I'm trying to show here, well, that will buckle under its own weight, especially in the beginning when the propellant is very significant percentage of the overall mass. And then the flexible body effects will come. This long, thin blue missile that you see here cannot be treated as a rigid body, and the model itself has to be augmented. So, all these things must be considered, and we must have solutions for these situations as far as possible. That's what I'm trying to uh, point out. Well, you are free to ask questions even during the lecture. So if someone feels like asking a question, maybe you intimate in whatever way that is possible. Amruta may be able to tell you. So there's no need to hold your questions at the end. Of course, we will answer questions at the end as well. Okay, so we continue. Therefore, we formally now talk about the plant because that is what we are interested in. Control is something that we are going to design, and uncertainties and disturbances is what are the adversaries against which we have to design our control. So, uncertainties in terms of parameter variations, unmeasurable disturbances, unmodeled dynamics. Sometimes some dynamics is so fast that we don't care to model it at all. An amplifier, for example. Amplifier is also a first order differential equation governed system. But the system is so fast that we ignore its transfer function or differential equation. That differential equation can become important if you are ambitious in your control. So once again, the interplay between control and modeling. Unmodeled dynamics, sensor noise, a hard question for feedback control engineer, because feedback control engineer depends on what the sensor tells him about the status of the system. If that sensor does not give him the correct information, then he is at a great loss. So, sensor is something like the state that is known or observed by the system. And if you get corrupted in that, well, your chances of being able to control the system pretty well will be rather difficult. So the uncertainties are once again classified as structured, where you have parameter variations, etc., but no additional dynamics. Unstructured means there was some additional dynamics, which was ignored, like unmodeled actuator, unmodeled sensor, or flexible body effects about which we just talked in terms of a long, thin missile. The disturbances are external and unmeasurable. So these are the adversaries against which we have to design our control law. Just to give an analogy to unmodeled dynamics, it is whatever we said that is repeated here. So the dynamics that really exists but was ignored by the designer. And this ignoring of the dynamics will be okay provided you don't excite it. So this comes in fast actuator sensors, and the prudent action is not to excite that fast dynamics. By analogy, I have put a sleeping dog here. As the proverb goes, let the sleeping dogs lie, don't wake them up. Similarly, unmodeled dynamics is of that type. Okay, the control strategies that are prevalent, very common control strategies: linear quadratic regulator, where the strategy works fine, excellent result, beautiful solutions, but for plants with no uncertainty. So that is something that discourages us from using linear quadratic regulator in the absence of any robust technique. The linear quadratic regulator is an elegant solution, but for practical systems, it is not very well suited. And this was analyzed for its use in missiles in a very famous paper in 1984, where they showed that modern control, just applied without thought about the practical aspects, might fail in practice. Adaptive control, a strategy to estimate uncertain parameters online, but it demands a model and must not have unstructured uncertainties. That is, must not have unmodeled dynamics. It is highly sensitive to unmodeled dynamics. Uh, in fact, adaptive controls were developed in the uh, 70s, in the decade between 1970 to 80. Adaptive control, lot of work was done, and again, one person showed that adaptive control algorithms can become unstable in the presence of unmodeled dynamics. So that actually gave a big jolt to the adaptive control community, and they developed laws where adaptive control can work in the presence of unmodeled dynamics, but still some problems remain, and therefore adaptive control must be used with caution. Some strategies which sort of virtually alter the plant.
Oh,
Yeah,
sir.
yes. Hello. Am I audible?
Yes, sir.
Yeah, I thought somebody had a question.
Sir,
Any question from audience?
sir, I have a yes, ma'am. I have one question.
Yes,
Yes, you are
please.
audible, Dr. Shah.
Yeah, please ask.
Sir, in the last slide of adaptive control, you have mentioned the structured uncertainty.
Yes. That means I know the order of the system, but I don't know the values of parameters. That is structured uncertainty. So in such situations, adaptive control will work fine. Okay. Okay, so model following control, where we shape the plant. The real plant is here, and I have got a model in the sense of something that I desire. I would have liked the plant performance to be like the performance of the model here. And therefore, a model following control is designed so that the plant performance is like the model performance. This is something that in effect changes the plant. So model following strategies are used and they are popular even today. The sliding mode control, about which we will be talking in greater details, only bounds of uncertainty are required. In this case, control is basically discontinuous. So the control is not a smooth control, and that is a big drawback of sliding mode control. A discontinuous control can excite fast on model dynamics and can make the system unstable. So one thing leads to another, and smoothing approximation to overcome the drawback is what is required. So we'll be talking about these uh, issues in greater detail later. Sliding mode control, the main advantage is that it requires only the bounds of uncertainty. So that's a great advance compared to whatever strategies were developed earlier using lead lag networks or PID control, etc., etc. Compared to that, this represented a greater advance. Apart from,
Sir,
yes, yes,
uh, sir, regarding the bounds of uncertainty,
yes,
lower bound and upper bound. Uh,
yes.
so in my one ISA transaction paper, I have specified the lower and upper bounds for the controller parameters.
Huh.
Sir, basically, there must be a systematic procedure to specify the lower and upper bounds. So, on what basis? Because we don't know the upper bounds, sir, for the controller parameter or plant parameter. Is there any way to decide the lower and upper bounds of the controller parameter, or which methods are used to specify
Yeah.
the bounds?
Yes, we'll come to that. But before we can answer your question, we'll have to talk about the upper and lower bounds of the controller parameters. I think the rest of the audience does not have background in sliding mode control,
Yeah.
and therefore I'll reserve your question for a later discussion. We'll
Yes,
come
sir.
to it.
Yes, sir. Yes.
Is it Dr. Laure?
Yeah, yeah, sir. I'm your student, sir.
I could recognize your voice.
Yeah.
Okay, so we'll come back to that.
Okay, sir. Okay, okay.
Yeah. Okay. Now, apart from sliding mode control and whatever methods we have discussed so far, there are other methods like the fuzzy control and neural networks, where the model itself is not assumed. And they are becoming popular these days, although with fuzzy control, there are difficulties in giving stability proofs, but that takes us to the era of James Watt, where he designed the system without having a model. So sometimes things go back and forth, and that is quite interesting. Unfortunately, we'll not be talking about fuzzy control here. The next thing that I would like to talk is the disturbance observer, where rather than talking about the bounds of uncertainties, we estimate the uncertainty itself. So the basic principle of disturbance observer is to estimate the uncertainties. Estimate the uncertainties, use that estimate in control so as to negate, to annul the effect of the uncertainties. The control is smooth and works with systems which are called the minimum phase systems, which have no right half poles or zeros. The basic method has a drawback of working with slow varying uncertainties, but extension is possible when uncertainties are rather fast. So, a combination of disturbance observer and sliding mode control is something that shows great promise. I suppose in the next lecture, Dr. Amruta Deshpande will be talking about applications of disturbance observer to MPPT, and some other fields. So disturbance observer together with sliding mode control is a very promising uh, area. Okay, now we come to sliding mode control. The sliding mode control was originally called a variable structure control because some feedback connections get changed. Some feedback goes from positive to negative, or some gains change during the operation automatically. And these systems are called variable structure control systems. But variable structure control systems do not give us freedom from the uncertainties. They have some uh, favorable properties, but sliding mode control is something that guarantees invariance. That means with sliding mode control, you can say that the performance of the given system will be such and such in spite of the presence of uncertainties. So that's the beauty of sliding mode control. The idea of sliding mode control, let us say that we have a second order system with x1 dot equal to x2 and x2 dot equal to some other uh, dynamics. The system can be represented in the plane of x1 x2 state variables, the state variable model that I'm considering here. And I draw a line in this plane which you are seeing as the sigma line. This line which you are seeing here, I'm drawing a line parallel to it. Well, this line is called the sigma line. On one side of this sigma line, sigma is greater than 0. On the other side, sigma is less than 0. Now, what I want to do is, when a system trajectory starts from somewhere in this plane, it should be attracted. Suppose it starts from here. I'll try my hand. Goes like this. It should be attracted by the switching line, by this sigma line. If it goes on the other side, even then it should be attracted. That is what I want. How will that be possible? When sigma is greater than 0, this motion, when it comes from a point like this and then remains on this line, this second motion where it is just embracing the sigma line is called the sliding motion. For sliding to occur, what must happen? If sigma is greater than 1, sorry, if sigma is greater than 0, then what must happen so that the trajectory will come onto this sigma line where my green trajectory is now actually very close to it? The rate of change of sigma must be negative. If sigma is greater than 0 and the rate of change of sigma is negative, the trajectory will come towards the sigma line. On the other hand, if sigma is less than 0, that is, I'm somewhere on this line, on this side, then sigma dot should be greater than 0. And if we express this as one single condition, that will be sigma sigma dot less than 0 will make the trajectory be attracted by the sigma line. So this sigma sigma dot less than 0 is the most important condition in sliding mode control. Now, the beauty of design of sliding mode control is that I can enforce this condition even in the absence of precise or exact knowledge of the parameters of the system, which are uncertain, and therefore it is not possible to have a precise knowledge of them. In spite of that ignorance, I'll be able to make this condition possible. The trajectory starting from somewhere will come and hit the sigma line and then will remain on the sigma line. My hand is not steady. Assume that it is very, very close to the sigma line. Then after it hits the sigma line, it will behave like the sigma line itself. And the sigma line will now decide the operation of the system. That will govern the performance of the system. And therefore, we will get invariance. Let's see how it happens. If the switching, when it goes from one side to another, if the switching occurs at a slow frequency, we'll get something like this. This trajectory comes here, hits the sigma line, goes off it, is thrown back to it, etc., etc. So this is practical switching. When the switching cannot be done at infinite frequency, we might get a situation like this. With practical switching, when the control does not switch to a new value sufficiently quickly, the trajectory does leave the sliding line at certain instants of time, like the instant here, here, etc. But it is still very close to the sigma line, and therefore a modest invariance is obtained. So when the trajectory leaves the sliding line, it is mildly dependent on system parameters. On the other hand, if the switching is ideal, that is a situation like this trajectory starting from P is going to Q, hitting the sigma line, and after that it goes along QO. So it remains on the sigma line. So in such a situation, once the trajectory hits the sliding line, it is constrained to lie on it. That means it is constrained to lie along QO. The system dynamics is governed by the equation of the sliding line. Whatever equation we have, we'll of course talk about that equation. So in such a situation, the system
Sir,
is totally insensitive to system parameters.
sir,
What we
excuse me to interrupt you, sir. Can you
yeah.
kindly tell me how to choose this sigma line? Actually, what is sigma? Sigma is this the real part of the pose, right, sir, or something else?
No. Sigma is name given to this line. So this line which you are seeing now, QO, is
Mhm.
a line going through the origin, and it can be written as C1x1 plus x2.
Oh, sir, how to choose that particular line?
Yeah. So we'll talk about it.
Okay, sir.
Yeah. Okay. I think I'll have an answer in my presentation. If it is not there, I'll answer your question later. Okay. Yeah. So let us take an example. Now, I'm taking a simple example and we are working through that example so that you will be able to design a sliding mode control for a second order system at least, and later for higher order systems. So we are going through the steps of design so that there is no mystery in sliding mode control. So let us see the description. I got a system, second order system, x1 dot equal to x2, x2 dot equal to minus a1, x1 minus a2, x2 plus bu, and the parameters a1, a2, and b are uncertain. Uncertain, but I know the range in which these parameters lie. I have got some knowledge of these parameters. They are not totally unknown to me. What is that? The values of the parameters are unknown, but they lie in known ranges, meaning this parameter a1 is known to lie between a1 under bar to a1 over bar, where a1 under bar and a1 over bar are known to me. Suppose you have a resistance, then you generally know that the value of the resistance may be between 80 ohms to 120 ohms. We don't know exact value, but we know that it lies in a certain range. So this crude knowledge about the system parameters is generally with us. Later on, we'll overcome this difficulty also. Even if we don't know anything about the parameters, can we still control? Yes, but that will come later. Similarly, A2. I know the upper bound and lower bound and upper bound in which this parameter lies. And the same goes with B. I know the range in which B lies. So that's my knowledge. The parameters are uncertain. I don't know their exact values, but I do know the range in which the parameters lie. Okay. Now, what is the objective of control? Design a control so that the system trajectory starting from anywhere in the x1, x2 plane will hit the sigma line and will then slide along it. Okay. So we define a sliding line. This sliding line is defined as C1 x1 plus x2, where C1 greater than 0 is a user chosen constant. This is something that I have chosen. As far as the system parameters are concerned, A1, A2, and B, I have not chosen them and I don't know what their exact values are. Is that okay? Please absolutely feel free to stop me and ask your questions, because if you understand the basic design of sliding mode control, I think the purpose of this lecture will be more than served. So don't hesitate to ask your questions. Okay, next, for sliding to occur, control must be designed so that the sliding condition is satisfied. That is, sigma dot must be made less than 0. We'll see exactly how we can do it. Okay, just for the sake of reference, the first things are repeated. So this is our system. A1, A2, and B are unknown parameters to us, uncertain parameters, but know the ranges. This is what I have chosen. C1 is my choice. Our friend has asked as to how to choose this line. We'll talk about it a little later. And the way to bring the trajectory of the system onto the sigma line is to design a control so that sigma dot is less than 0. Okay. So first step will be to get sigma dot, and by the equations which are in front of you, it's straightforward and easy. So if you concentrate, you will understand all the equations that we are going to write in next 10 minutes. So sigma dot C1 x1 plus x2 dot. Next, just substituted the values. I given the detailed workout, so even if there is some gap in the lecture now, later on when you read these notes, you will be able to get everything. So all equations are written down here. I'm not skipping any. Now consider a general form of U. I have to design a U so that sigma dot will be less than 0. That's my objective. So how will I design U? What I have in my hands? In my hand, I have got only the sensors, measurement given by the sensors. And sensors will measure the states, that is x1 and x2. I will use x1 and x2 to design the control, and a general form of U will be U equal to psi1 x1 plus psi2 x2, where psi1 and psi2 are gains, something like amplifier gains or feedback gains, state feedback for people who are familiar with state feedback control. Psi1, psi2, using the U that you see in equation 10, I put that in the expression for sigma dot in 9 and get this. So sigma dot is obtained. Very straightforward. Repeating the last lines. Now, I got sigma dot. I want sigma dot less than 0. Therefore, I will get sigma dot now from the equation that you see on top. So sigma dot is here. In sigma sigma dot, there are two terms. I want to make sigma sigma dot less than 0 by using control, that is by designing psi1 and psi2. I want to make sigma sigma dot less than 0. Obviously, if each of these terms, which are put in under braces, each is negative, certainly sigma sigma dot will be less than 0. I'll make life simpler by calling those terms as y1, y2. y1 is the first term, y2 is the second term. For satisfying the sliding condition, sigma sigma dot is to be made negative, and therefore I would try to make both y1 as well as y2 independently negative. That may be an overkill, but a simpler procedure. So consider y1. For y1 to be less than 0, you can see equation 14. The right hand side of equation 14 must be less than 0. Now when x1 sigma in that is greater than 0, then y1 will be less than 0 if b psi1 minus a1 is less than 0. That is, psi1 should be less than a1 by b. Straightforward. Just put a1 on the other side and get this condition. When x1 sigma is less than 0, y1 still has to be made less than 0, and that will happen if b psi1 minus a1 is greater than 0. That is, psi1 greater than a1 by b. We have got a funny condition here. If I want to make y1 negative when x1 sigma is greater than 0, I have to make psi1 less than a1 by b. And otherwise, I have to make psi1 greater than a1 by b. So obviously, a constant value of psi1 will not work. So how to choose psi1? A fixed value is not going to work. Therefore, I make a value of psi1 equal to alpha 1 depending upon this condition. If x1 sigma is greater than 0, then I will take it as alpha 1. If it is less than 0, I'll take it as beta 1. Now I'll be able to satisfy these conditions. So, if psi1 is equal to alpha 1 should be less than a1 by b rather than psi1. And similarly, beta 1 should be greater than a1 by b. And I'm going to switch the value of psi1 between alpha 1 and beta 1 depending upon the sign of x1 sigma. If it is positive, one value. If it is negative, another value. Okay? So, coming back to this, well, repeating all those terms just for easy reference. Now we are concentrating on y2. A similar logic holds good for y2. So I'll just skip it. You'll be able to read it comfortably if it is not clear now. So again, for psi2, I cannot use a single value and I have to switch psi2 depending upon the sign of x1, x2 sigma. And then I'll be able to satisfy it. That is also shown here, worked out. So having chosen psi1, psi2, that is alpha 1, alpha 2, beta 1, beta 2, depending upon the sign of x2 sigma, I am able to make sigma sigma dot less than 0. If sigma sigma dot is less than 0, sigma goes to 0. And then the system behaves like the user chosen C1 x1 plus x1 dot equal to 0 system. And that is how the invariance, insensitivity to the uncertainties happens. A generalization is being discussed next. So if I have an nth order system, well, my sliding surface will have n terms and control law will also have n terms that you see here. There will be switchings between alphas and betas, I going from 1 to n. Well, the generalization actually tells us that the method that we just discussed is a tedious method when the system is of higher order. So we'll work out a solution for that, a remedy for that. But before we go on to that, the control that we designed, what did it produce? Well, the x1, x2 plane in the first place, that is this figure that you see here. Well, from this point to this point, the blue trajectory is the reaching phase. The trajectory is reaching the sliding line. From here, it goes to the origin along the sigma line, the red line that you see here. I am now crossing it here. So this line is the sigma line, and that takes it to the origin. You can see that once it hits the once it hits the sliding line, it does not leave it and goes to the sigma line, goes to the origin. So it is in this portion that it behaves like the system x1 dot plus c1 x1 equal to 0. The control, which had to switch between alphas and betas, is discontinuous, and that is apparent from the plot of U. You can see that the control has very rapidly changed from one value to another, and that is this discontinuous behavior, a chatter in control, which is greatly objectionable. In fact, sliding mode control did not become popular in the beginning because of this reason, that the control was a chattering control, discontinuous control. We have worked out a solution. So, okay, so the x1 and x2, well, they approach in this way. Sigma, as you can see, starts from a non-zero value, and when the trajectory is on the sigma line, well, sigma is 0. As you can see, sigma has just gone to 0. So this is how the results will be. Okay, discussion. As the system order increases, the design becomes more complicated. The mechanization becomes more complicated because of number of switches, and we have to calculate the value of psi I for I equal to 1 to n. That is a very tedious thing. A simple generalization is desirable, so we'll think about that. The control U ensures sigma sigma dot less than 0. When sigma dot is less than 0, sigma goes to 0. When sigma goes to 0, c1 x1 plus x2 goes to 0. And notice the first equation, x1 dot equal to x2. So using that, c1 x1 plus x1 dot equal to 0. And therefore, if I solve this, x1t equal to x1 0 e raised to minus c1t. Now, our friend had asked as to how to choose this sigma line. If I choose a sigma line like this, I'll try to draw it here. Okay, now if I choose a sigma line like this, the value of C1 for this line will be negative. Suppose it is making an angle of 45 degrees, C1 will be equal to minus 1. If I take this sigma line, what will happen to this equation x1t equal to x1 0 e raised to minus c1t? With c1 equal to minus 1, this will become unstable because e raised to t will go on diverging as t progresses. Therefore, I cannot use a sigma line that passes through the first and third quadrant. I must take a sigma line that goes from the second and fourth quadrant like this. That is for sure, for stability. Next question is, should I take the line like this or closer? Sorry. Or a line closer to the y-axis with greater value of C1. For this line, C1 value will be greater. If C1 value is greater, then the trajectory will take x1 to 0 faster. But the magnitude of control will be more. So how to choose the sigma line depends upon your objectives, how fast you want the trajectory to go to the origin, and how much control effort is possible depending upon the power of the actuator. So that's a matter to be decided depending upon the application. But one thing is sure, you must choose C1 such that this equation is stable. To that extent, I suppose I have answered the question. Does that answer your question, or you still have something to ask about how to choose the sigma line?
Okay, sir, I have got.
Yeah. Okay. Yeah. Right. So insensitivity to the system parameters in sliding mode, only in sliding mode, not in the reaching phase. The reaching phase, which we saw earlier, during that phase, the system is sensitive to system parameters. And therefore, we note some points. The nature of control is discontinuous. The order of the system is reduced. Look, the original system was second order. When it was in sliding mode, it behaved like a first order system. The order of the system was reduced by 1, which is equal to the number of inputs. The number of structures, well, that depends on the number of states. How to generalize for higher order systems? This form is not good. Actually, the answer to this question, next question, fifth question, is this form is not good. It is a cumbersome form. And can we think of something better? Shall we have some more time and finish this part? I think we'll need, what's the time now? I think we still have time to
Yes,
go to the end. So a simple example, I'm considering uncertainty only in A. But of course, we can consider uncertainties in other matrices like the B matrix and also the external disturbance. That is also possible. But just to make life simpler, I'm just considering the uncertainty in A, which is called the delta A is the uncertainty. Next, the assumption delta A has to have a certain form, and that form is called matching condition. So this is another thing that we have to consider. The uncertainties delta A have to satisfy a condition like this, B into D, where D is an unknown matrix. So uncertainty is still present, but a form is assumed. The system now becomes, when I put delta A equal to BD and call that dx as ext, I'm calling it as the lumped uncertainty. My original system now looks like this system. X dot equal to ax plus bu plus be. I make an assumption. I had earlier assumed that I know the bound of uncertainties. Well, now the size of uncertainty is a similar assumption, and I'm saying that the uncertainty is bounded by a rho function where rho is a known positive scalar function. The switching surface C1x1 plus x2 was the switching line. Well, that can be generalized by putting it as sigma equal to Sx. And for our previous example, S would be a row vector C11 and X will of course be a column vector x1, x2. Design of control. The sliding condition is sigma dot less than 0. So the control should be designed so that the sliding condition is satisfied. I get sigma dot equal to Sx dot. Substitute the values, straightforward design. S into round brackets ax plus bu plus be. I split my control into two parts. One for catering to known things and the other part catering to the unknown things. So now selecting u equal to u equivalent plus un and putting it in sigma dot equation sax plus sbu equivalent plus SBE. Well, I have made a mistake here. There should be UN also. U equivalent is chosen so that SAX plus SBU equivalent goes to 0. There is one more term here. I'll put it. Well, this SBUN plus SBE. SBE is already there. SBUN was missing here. Okay. So there is a correction, typo here. Now selecting U equivalent equal to this, by putting it here, I get sigma dot equal to SBUN plus SBE. Sigma dot sigma SBUN plus sigma SBE, which is less than or equal to, by using the standard rules, standard inequalities, sigma SBE will be smaller than absolute value of sigma SB into absolute value of E. That is smaller, once again, by absolute value of sigma SB, and mod E we have assumed is smaller than the rho function. So rho. Now selecting UN as minus rho signum of sigma SB, I get sigma dot less than 0. Thus, the sliding mode is guaranteed. Okay, so I think now we don't have time for this lecture. So we'll meet in the afternoon. So some more part of sliding mode control is yet to be covered along with disturbance observer. So that part we'll cover in the lecture that starts at 2:30. Am I right?
Yes, sir.
Okay. Yeah. So till then, see you again.
Thank you, sir. Thank you so much for such wonderful details related with the control, sliding mode control. The request for the audience that we will be starting our next session at 11:45 sharp. So be there. Thank you so much.